All right, so welcome to the videos for Unit 9. This is the first one for Section 9.1, Inverses of Functions. What on earth is an inverse? We're going to look at this through a geometric viewpoint, okay? This first example is going to be able to kind of define what an inverse is. So let's just jump right into this example. Graph the reflection of the point 4, 5 across the x-axis, the y-axis, and the line y equals x. Then write the coordinate of the new transform point in each case. So let's go ahead and do that now. We'll just give ourselves some graphing lines. We have no idea what's going to come out of this, but we'll start with some axes, and we can graph the point over 4, up 5 on this graph here. 4, 5. Let's do that with each of them now. Because we are going to end up doing this 3 times, we may as well graph that point 3 times. Whoops, sorry. Out 4, up 5 would be right there. And then last one. Out 4, up, up 5 would be right there. Okay, so we have the same graph 3 times, right? Now let's start doing stuff to it. So the first one, they want us to graph the reflection of this point over the x-axis. Well, the x-axis, we know, is the horizontal one. So just like looking into a lake there, it's going to jump over the x-axis, head down to here. It's going to be in the same spot, but across the line. So what is this new point? This new point would be the same x value, right? It's still the same over, but the y value has now flipped upside down to -5. So when we are reflecting over the x-axis, we see that y value change. Going over here, what would happen if we did the same but opposite? What if we did the y-axis? Well, it's less like looking in a lake and more like looking in a mirror. We would jump this way. And we would be here using the y-axis as the mirror. It'd be in the same spot, right, but flipped over. And this time the y-axis, or sorry, the y value would remain the same, right, because it's still the same up and down, but now it's a -4x. So when you have a reflection over an x-axis, your y changes. When you have a reflection over a y-axis, your x changes. What happens, though, when you reflect over a different line, a line that is not an axis? Well, the line y equals x, don't let that scare you. It's not a super fancy line. It's actually the most basic of lines we have. For some of us who are really, really ingrained in y equals mx plus b, this is a linear. I know it's a linear because there's a power of 1 here, but the slope of 1 and an x-intercept of 0. So it's the most basic linear you can find. Another way to look at it is the line where all of the x's match the y's. So 1, 1, 2, 2, 3, 3, 1.5, 1.5, all of the ones that match. Now we know 4, 5 is not on that line because 4 does not equal 5, right? So 4, 5 is not a solution to this line. It's not actually on that red line there. But what happens when you jump over that? If you were to use that red line as a mirror, I don't like my line that much. Hold on. It's a little sloppy. Because it's kind of tight here, right? We want to make sure, whoops, what did I just do? Okay, let's make it a little more accurate there. It's kind of tight. 4, 5 is pretty close. So what happens when you do jump over that line? You jump over, you would get right about here. Well, what is that point? It's not a negative version of anything, right? Because we're still in the first quadrant. So what point is this? We go out 1, 2, 3, 4, 5, up 1, 2, 3, 4. Interesting. By jumping over the line 4, 5, we have switched the point to 5, 4. Now, while these two reflections are very nice, this last one is what we call the inverse. Notice the inversion of the point. The x has become the y has become the x. And so this would be the inverse graph. All right, let's look at that with another point. We'll even use the same graph. Does this work for everything? So let me continue drawing my line here. Let's do a point that is negative. Would the same thing happen? Let's choose, I don't know, this one right here. That would be the point back 3, up 1, so -3, 1. If I were to jump over this line, I would go ... 2 down to it, and therefore ... 2 down from it, right? Because it's like a mirror, still looking in that mirror. And where do we end up? We end up +1 down 3. So even with negatives, we see that inverted point. We didn't change the signs on anything, but by jumping over this red line, we have changed spots, right? Now, with any reflection, if you are on the line, you should stay the same. So what about this point here? What about this point negative, well, yeah, -4, -4? Well, when you switch the values on that, what happens? You get -4, -4 because they equal each other. So even so, we can still invert there. Now we could build on this idea instead of just singleton points. Remember that points are parts of equations. They're answers to equations. So you could, in a sense, take a whole mess of points and invert them at the same time. You could invert a whole function. We could take f here in red, right? We could take this f function, which is a cubic, right? We've seen this before. It's got that nice little bump in the middle of it. But we don't have to use that to invert it. We could just say, okay, well, here's a point 0, 2. If I invert it, look at that. It ends up over here at 2, 0. If I were to take the point, what looks like 1, 4, and I flip it over, I get 4, 1. And we could keep doing that with every single point, even the ones that are not whole numbers. I could do 1.5, comma, what is that, 3 through 2/3, something like that. 2 and 2/3. I'd flip it over and I'd get that 2 and 2/3, 1.5, right? It flips over the same way. And so you could graph the whole thing. You could invert the whole function. All right, that is what an inverse is. We're going to go see if we can prove if two lines are an inverse in the next video, and I'll see you there.